So welcome student for today's lecture. So recall that in our last um, lecture we discussed about normal subgroup. Okay, so satisfy one of those equivalent conditions. Okay, there are few equivalent conditions, and there are more actually. I know I only list down 5 or 6. So it satisfy any of those things called normal subgroup, and then we define the left cosets. So left cosets are what? This is kind of equivalent classes with respect to some equivalent relation which we already defined, right? So left cosets, and then what we did, we define a operation on this set by this, that g1h dot g2h by this g1 g2 of h, right? And we showed that this operation is well defined and it satisfies all the properties of the group. So it makes G mod H is a group, and this group we call quotient group or factor group. Okay, that we already discussed yesterday, or rather our last class. Okay, now you can think a little bit more about this. So we can, because the GH left cosets are actually equivalent classes, so we can write down that your group G is a disjoint union. So this is the symbol of disjoint union. So disjoint union of GH, G belongs to G. So what does that mean? That means uh, these are all distinct. Okay, G is a representative where distinct representative of these cosets. Okay, so what does that mean? That means if you say, so you have a group G and you have this small cosets. So G1H, G2H, and so on. Okay, something GKH, so on. I don't know how many such are there. Okay, and these are disjoint unions. So what does that mean? That means if you want to find out how many elements are there. Okay, so I'm assuming that. So I'm assuming um, that the G is finite. Okay, if G is not finite, then also this relation is true. But if G is finite, you can count it actually. Okay, so if G is finite, then you just write down this by this notation. This cardinality of G is nothing but a sum of our cardinality of this, right? G belongs to G. And this sum, I can write down star. Star means that the G is all distinct representative, okay, of this left cosets. Okay, so number of elements inside G is nothing but the sum of the number of elements inside the left cosets. Okay, distinct left cosets. Now the question is that for any element G, what is the number of elements inside the cosets? And so let us now try to think whether this is known or not. So claim is that this number is exactly number of elements inside H. This is the claim. Okay, now how to prove that two? So as I said, they have same elements. What does that mean? So you can find out a bijective map from one to another, right? So how to find out? So let me give you a map, say for example F from H to GH by, so let me define this f of H is going to GH. Okay, and let us check that this map is a bijective map or not, then we are done. Okay, so how do you check this map is bijective map? So this is obvious. So this is injective. So so let us check it. Injective. How to check injectivity? So let f of h1 equal to f of h2. Okay, h1 h2 belongs to h. Okay, Suppose we have two such elements, and then this implies GH1 equal to GH2, right? But you know that G inverse exists inside G, so it's know that G inverse exists in G. So what does that mean? That means you can multiply by G inverse and then it will give you H1 equal to H2. So that is the proof of injectivity. So this map is injective means obviously with finite size injectivity is equal to surjectivity, but let us also prove the surjectivity. Doesn't matter. So but I mean, yeah, so even you don't need anything. So surjectivity is by definition. So elements of this set of the form GH, so subjectivity is actually by definition. An element of GH is of this form, G small h belongs to H. Okay, so this map is bijective map, and hence, thus, what you get? You have that cardinality of H is same as cardinality of GH for any G belongs to G. Okay, so that originally the cardinality of G is nothing but summation H. Okay, and this number, so this is star. Okay, so this is a number. So how many such G's are there which are for which GH is distinct? That number. So now define it. So we define this number, that number of distinct left cosets of H in G. This is my number. This is called this is the number of distinct left cosets. You can I mean, there is nothing special about left. You can do it by right also. Okay, so I'm just doing it by left cosets. Left cosets of H in G, and this number is called the index of H in G. Okay, so thus what you can write down? Finally, you can write down that cardinality of G is nothing but index of G H mod G into cardinality of H. Okay, now this is not a universal notation. Some people write down by these, some people write down by cardinality of G mod H. I mean, okay, so you can use any of the symbols. Okay, clear. So this is the symbol that the number of distinct left cosets is written by this symbol. Okay, so what is the crux of the matter? The crux of the matter is that you can write down for finite group, you can write down this G in terms of number of distinct left cosets into the number of element in H. So what does that mean? That means the number of element in H, a number of or order of a subgroup, which always divides the order of the group, right? And this is a classical theorem. It's probably the first biggest theorem, so I should write down the name. It's called Lagrange's theorem. Lagrange's theorem. Okay. So how do I write down properly? So it says that let G be a finite group and H be a subgroup of G. Okay. Then order of H divides order of G. This is simple. Okay. So okay. So and also this, in this case you can write down that this, the index, the number of uh, this order of G mod H, which is the index. I just define it, and this number is, you check from this number is G mod H, current of G mod current of H for the finite number. I mean, obviously I'm assuming the finite group. Okay, clear? And this is called Lagrange's theorem, that tells you that whenever you have a subgroup of finite group, the number of elements inside the subgroup must divide the number of elements inside the group G, right? And obviously there are lots of applications, lots of corollaries. So the first corollary, immediately you can write down corollary 1. So you have a so you start with a finite group G and an element inside the group G, and then the order of the element X divides the order of the group G. Okay. And now this is obvious. So the obvious from this Lagrange's theorem, because you start with the group H, which is generated by X. What does that mean? That means H is a subgroup which is generated by single element. So H is a cyclic subgroup of the G, right? And in this case, we already proved that order of H is nothing but order of, right? In fact, we proved that this is actually identity x to the power whatever. If the order is n, then this is x to the power n minus 1. Okay, we already know these things. This is already proved. Okay, and thus order of x, which is nothing but current of h, and you know that this divides the order of the group G. So QED, this will. Okay, so these are all simple observation corollary. So you can have many such corollaries. Maybe corollary 2. Let me write down one more. Okay, so is important question that suppose you have a group G whose order is prime. Okay, so the number of elements inside the group G is some prime number. So this is prime number. I hope everybody knows what is prime number. Okay, then actually you can prove that G is cyclic. Then this G is a cyclic group. What does that mean? That means G is generated by a single element. Okay. And how to prove this? So prove simple also. So there are p many elements, right? So G is non-empty. So let you choose one element. So G belongs to G. Because G is non-empty, you can always choose. And then you take the subgroup H generated by small group G. Clear? Yeah. But what Lagrange's theorem tells? So now by Lagrange's theorem, what do you know? You know that order of the small g, which is nothing but curvature of h, which divides the order of group, which is nothing but the prime number, right? Now we know that okay, so I am choosing g not equal to identity. Okay, so I should write down that g not equal to identity, non-identity element. Okay, so order of g divides p, right? And p is a prime number. So either this is 1 order of g, or order of g is p, but it cannot be 1 because it's not identity element. So order of small g equal to p as g not equal to identity. Clear? So what does that mean? That means these non-identity elements is having order p. So order of the small element is exactly same as the coordinate of the, right? Clear? And thus hence this group G is generated by a single element. They have same number of elements, right? And one is after another, so done. So there are several such corollaries you can easily find out from here. Okay, so yes, so this is the powerfulness of this theorem. Now let us discuss some more nice ideas. Okay, so let me start with the definition. Okay, so suppose you have a group G and you have two subgroups H and K, and they are subgroups of G. This is given to you. Okay, and then we define something called HK, and this is the product of two. This is smallest set containing H and K, and this is by definition small h, small k, such that small h belongs to capital H and small k belongs to capital K. Okay, this is the set. And now you ask that how big is this set? Okay, so yeah, so I'm assuming that this is finite. So if it is finite, then only you will get this nice identity. Okay, so you ask that question, how big is HK? So what is the number of elements inside HK? How many such elements are there? Okay, so let us discuss. So it is actually, yeah, so its proposition is actually uh, is very nice identity. This number of elements is actually nothing but same as number of elements inside H into number of elements inside K divided by the intersection H intersection K. Okay, this number. Okay, so you need a proof, obviously. So don't believe anything without a proof. So you can use two ways of writing these things. So let me first write down HK as kind of union of distinct left cosets of K. So let me write down by this notion. So union of say H and K, H belongs to H. Okay, so this HK are cosets of K, right? Now what is known about these things? The first thing is you know that see this is I am not writing that these are all distinct, that H. Okay, so I need to find out that how many of these may not be distinct, that I need to find out. Okay, but what is known, the known fact is that this number of elements is exactly K. This is known to us. Okay, so it is now enough to know that how many such distinct left cosets are there of this form. Okay, so this is so if we have to find out these, this will be nothing but the sum over K. This I'm writing star means what? So I want to know how many distinct left cosets are there of the form that HK. Okay, so this is my next goal, to find out such things. Now how to find out these things? So you need to check that uh, under what condition two left cosets are equal. So we know that we know that if h1k equal to h2k for some h1 h2 belongs to h, then what happen? Then this implies uh, that h2 inverse h1 is an element of k, right? This is property of cosets. So h21 h element of k, and again h2 inverse h1 is element of h, because h is a subgroup. So this is element of k intersection h, or rather h, whatever, h intersection k, doesn't matter how. Okay, so what does that mean? That means that, so this implies that h1k is same as h to k if and only if see, this is element of this. So what does that mean? That means h1 as a subgroup of cosets of hk equal to same as h2 cosets of hk. Okay, clear. So number of distinct cosets of k inside H. So we need to find out the number of C. This HK since H intersection K is a subgroup of H obviously. So thus the number of distinct left cosets of left cosets of HK in H is what? So this will be again we just prove it from Lagrange's theorem, right? So this is nothing but mod H divided by H intersection K, right? And thus we'll have uh, the number of element in this is nothing but, remember this sum, right? This sum and this K, right? But this sum is nothing but this, like number of such the sum is running over this number of elements, right? Number of such H for which Hk is distinct left cosets, and thus this will be nothing but mod H cardinality of K divided by cardinality of H intersection K. Okay, so this gives you a nice and clean way to find out this how many such elements are there in the product set, right? But another question is maybe the next proposition rise into our mind that what happen if are there any condition on HK for which this becomes a subgroup? So like uh, proposition 2, maybe I can ask like this, that under this question, proposition 2 highlight later, under what conditions is HK becomes a subgroup of G. Okay. See, HK is a subset of G obviously because H and K both are inside G and G is closed under multiplication, right? Closed under the operation. Okay, so obviously there are many such applications. So proposition, now let me write down that proposition 2, that HK is a subgroup of G if and only if what happens if they commute. So what does that mean? So HK equal to KH. This is a very nice statement, right? So if HK, see KH is exactly the same I can define. It is kind of product of the element of the form K into small k into small h, where small k belongs to small k, small h, small k belongs to capital K, and small h belongs to capital H, right? But they need not be same. In general, KH and HK need not be same, right? They have the same number of elements, but they need not be same, as I said. But if you, but we will going to prove that these two segments are equivalent. So if they are same, that will gives you a group structure on HK. If you have a group structure on HK, then HK and KH are same. Okay. Now you need a proof for this. So proof. So so you start with that HK is a subgroup of G. Okay, this is my statement. Okay, so let me start with this, and then what you need to prove? So you need to prove that KH and HK, they commute, K and H commute, right? But we know that both H and K both are actually subgroup of HK, because they are subset of HK. HK is bigger. HK contains, right? This is obvious that H is contained inside HK. Also K is contained inside HK, right? So what happened then? H and K, they are actually subset of this, right? So what does that mean? That means if both are subset of this, then you just I mean you just write down K into H, and then this is subset of HK, right? This implies this, because K subset of HK, H subset of HK, so the product is also subset of HK. Okay, and similar thing is true in the other way also, right? So similarly, HK also. Okay, so similar factor. Let me give a proof. So let me give a proof like this. That will be better. Uh, I should say without proof. I should not say. So again, what I need to prove? I need to prove that every element of this HK is inside of this form, right? So how to prove this? So let you choose an element HK belongs to H and K. Okay, and HK will be obviously the inverse exists, right? So you can write down HK is something, say, inverse of some element. So maybe some. Okay, so how do I write? So okay, so inverse of HK, maybe say something, say A, right? So what is nothing but K inverse. Okay, so yeah, so inverse of HK is A, which is also an element of HK, right? So it should be something, say H1 K1, right? Because inverse also inside HK. Now obviously you can write down HK as A inverse, right? HK inverse is A, means HK equal to A inverse, and A inverse is what? A inverse is nothing but H1 K1 whole inverse. But H1 K1 inverse is nothing but K1 inverse H1 inverse, right? And hence this is an element of KH, because K1 inverse is an element of K, H1 inverse is an element of H. So given any element of the form HK, that is also element of KH. So thus HK is a subset of KH. And done. So that means they are equal, they commute. As I said, they are equal, right? So this part is obvious. Now conversely, converse part is the important part. So conversely, let us assume that HK equal to, okay, so this is given. Now I need to prove that HK is a subgroup, right? So what does that mean? I need to prove that let something, say X and Y belongs to HK be two arbitrary elements, right? So let me start with two arbitrary elements. Now if I start with two arbitrary elements, then I need to prove what? I need to check that so xy inverse. So what I need to do, I need to check that. So we need to check whether xy inverse is an element of HK or not. Okay, this we need to check. Okay, now how to check it? So let me start with this. So x is element of HK, so we can write down as some h1 k1. Similarly, y you can write down some h2 k2. Okay, and then what happened? Then this thing happened. Then you can write down as uh, uh, x y inverse as h1 k1 into h2 k2 whole inverse. This is nothing but h1 k1 k2 inverse h2 inverse, right? Yeah, now this, look, this k1 k2 inverse is another element, say k3, so you can write down h1 k3 h2 inverse, right? Clear? And now also you know that hk commutes with kh, so hk equal to kh means what? That means this element you can write down something of the form that kh, one from k, another from h, right? So what you can write down, so you can or rather this element you can write down of this. Yeah, so let us write down this element. So as hk equal to kh, we have k3 h2 inverse equal to something, say h3 uh, some k4. Okay, for some h3 belongs to h and k4 belongs to k. Okay, so what happened then? This will be of the form that h1 h3 k4, but again h1 h3 is an element of h, so you can write down some h4 k4, right? Now which will be of the inside this set hk. So what happened then? Whenever you have x and y belongs to hk, you see the xy inverse also element of hk, and this is the proof. So this gives you thus hk is a subgroup of G, right? So apparently it look like that H and K are two different. If you choose to distinct two whatever different subgroups of G, it may not be may not form, say the product may not form, say subgroups, and you have a relation. The relation is that if they commutes, then they are going to form a subgroup, right? So this is commute. See, so when I'm saying commute, so I mean that as I said they are commuting, not as element. So this is, yeah, so I should say that not as an element. So it's an important remark. So remark. Okay, so H HK is KH as I said it does not mean that whenever, so H and K equal to KH for all H belongs to H and K belongs to K. No, it is not the meaning. Okay, does not mean. Okay, so what does that mean? That means HK will be some K1 H1. Okay, Yeah, for some special element it may be the same, like for maybe identity. If you choose h equal to identity, so then h into k will be k into identity. Okay, or if k equal to identity, the same thing will happen, right? So in general, this may not be this is true. Okay, and the second remark, obviously then hk is also a subgroup because hk equal to k, right? In that case, and hence the hk is also a subgroup of G. Okay, so here yeah, so one more important corollary you can find out from here, that from this theorem, the immediate corollary, what you can write down, you can write down that suppose we have h and k to subgroup of G. Okay, and you know something else, you know that h is sitting inside normalizer of k in G. Okay, and then hk is also a subgroup of G. This is the simple corollary. Okay, in particular, you can say that um, if k is a normal subgroup of G, and then this becomes full G. Okay, then hk again is a subgroup of ah, hk subgroup of G. Clear? For any, so in this case, see, if this is normal, then you choose any subgroup H. This always is true. Okay. So now, how do we prove this kind of corollary? The proof is also simple. So let us prove it. Okay. So so you already know that HK. No, what I need to prove? I need to prove that if so, let this is given. Let H is a subgroup of normalizer of K inside G. This is given. Okay, and then we will prove that HK. So we will prove that what I will prove, the hk and k are same, and thus that will gives you that hk is a subgroup of G, right? Now how do you prove this kind of statement? So so let you choose some element h belongs to h, arbitrary element, and k belongs to k, this arbitrary element, right? Now you remember that h is a subgroup of the normalizer of k in G. What does that mean? That means element of h normalize k, right? So so yeah, so element of h normalize k. So thus as h is a subgroup inside this normalizer of k in G, we have what do we have? See, normalizer of k in G is nothing but those elements which normalizes k, right? So what does that mean? That means h normalizes k. So h k h inverse is an element of k. This is given to you, right? And hence, obviously, if this is element of k, then you can write down as h. Yeah, so hk can be written as h k h inverse into h, because h inverse h will cancel and then become hk, but this is the element of k and this is the element of h, so this is an element of kh, right? So what I just proved, I proved that every element of hk, every element of hk is a element of kh, so hk is a subset of kh. Clear? Similarly, other way also you can prove. So similarly, how do you prove the other part? So similarly, Similarly, so if you start with kh, so kh you can write down as, see, remember, h normalizes k, so you can write down kh as h inverse into kh, right? Because this is identity, right? And this is nothing but h times h inverse kh. But this is an element of k, so this is element of h k, right? So every element of k is element of hk. So kh is a subset of hk plus hk, and k is the same as a set. Okay, and hence hk is a subgroup of G. And you see, we have one more condition here, that in particular, if k is a normal subgroup of G, then this. So if k is a normal subgroup, then what happen? Then normalizer of G in k. So k is a normal subgroup. So this normalizer is, so that means every element is normalizes k, right? This is the meaning of normal subgroup, right? So this is nothing but G itself, and obviously H is a subgroup. H is a subgroup of G, and then this condition trivially satisfied, right? Done. So so this is actually proof. Uh, okay, so maybe we may define one or two small thing today's lecture, and then we can finish it. Maybe we can give some exercise. Okay, so yeah, so you remember that we define something called normalizer, okay, and then center also define, okay, and one more thing, we should define something called centralizer, okay, 3 centralizer, centralizer of an element or as a set also. So so for an element, how to define centralizer of an element, say G of G. How to define it? So so it is defined by this symbol, this CGG, okay, and by definition, centralizer of G inside G is nothing but collection of all those elements, say G dash belongs to G, such that G commutes with G dash equal to G dash G. So centralizer is those elements commutes with the single element, right? So what does that mean? That means that see, for example, every element of the center belongs to the centralizer of any element, right? Because center, inside center, you have the element which commutes with every element of the group, and hence this is true. Similarly, you can also define for any set, for any so let me just do it subgroup is true for set also. You can define something called this, and this is collection of all such G dash belongs to G, such that G dash equal to G dash G for all G belongs to E. Okay, every element of it's commits with every element of A. Okay, these are my definition of normalization centralizer. Okay, now whatever we discussed so far, you can just work with some examples, and you see that for example, uh, suppose, so let me give some example. Suppose we have S3, this is our group G. S3 is a nice group. Okay, you remember that it has 6 elements: your identity, then these transpositions, which are 2 cycles. Okay, 1 3, and then 1 2 3, and then 1 3 2. Okay, and then suppose you have two subgroups. You took two subgroups, say H, which is generated by, say, um, 1 3 1 2, and K is generated by, say, 1 3. Okay, two subgroups. So you see, you remember that these two cycles are order 2 elements. So H is actually nothing but identity and 1 2, 1 2, and this is nothing but identity, case, and 1 3, because order of this H and K is 2, right? So you can ask, what about this? So that example tells you that this will be equal to this into H intersection K, right? But H intersection K is only identity is there, right? So this has to be 2 times 2 equal to 4. Now check it whether H K equal to 4 or not. H K is 4 or not. Okay. And what are the elements? So you have identity, and if you multiply by 1 2 with this, you have 1 2. Similarly, you have 1 3, and if you multiply by 1 2 1 3, then what will be the elements? The last elements is what? So 1 2 times 1 3 is what? So 1 goes to 3, 3 goes to 1 goes to 3, 3 goes to 3, 1 goes to 3, 3 goes to 1, 1 goes to 2. So this is 1 3 2. This is the element, right? And obviously this is not a subgroup, right? Yeah, this cannot be subgroup, because Lagrange theorem tells you that the order of the subgroup, this is not the subgroup of S3, because order of S3 is 6, order of HK is 4, so 4 does not divide 6, right? So this cannot be a subgroup. So you can use this kind of small ideas using Lagrange theorem to show that something is a subgroup or not. Okay. So yeah, so this ends our today's talk. So today we have focused on Lagrange's theorem, and we try to um, discuss the next step in next class. Okay, so do comment on the videos on the YouTube link. If you have any further question, I will try to answer as soon as possible. Okay, bye, thank you.